ERT 316, Reaction Engineering Chapter 2 Conversion and Reactor Sizing. Lecturer, Ms. Anisadika Ahmad. Email, anisadika@unimap.edu.my. Telephone, +604 976 8190. Outline Conversion Batch Reactor Design Equation. Flow Reactors Design Equations. CSTR, PFR, PBR. Sizing flow reactors. Reactors in series. Spacetime. Space velocity. 1. Conversion A greater than B, Smax, R equals 1 a B, Smax, Rev equals Shay. AA plus BBCC plus DD. Taking A as a basis. Conversion, SA, is the number of moles A that have reacted per mole of A fed to the system. A greater than B, Smax, R equals 1. A B, Smax, Rev equals Shay. Continuous flow reactor. 1. Conversion. Batch reactor. Continuous flow reactor. 2. Batch reactor design equation. Moles of A reacted. Middle dot. Moles of A reacted. Moles of A reacted / consumed, equals, moles of A fed. Moles of A fed. Middle dot. Moles of A reacted / consumed, equals, Na0, x. Moles of A that have been consumed by chemical reaction. Moles of A initially fed to reactor at T equals 0. Moles of A in reactor at time T. Na, Na0, Na0x. Na Na0, 1x. 2. Batch reactor design equation. Moles of A reacted. Na Na0 Na0x. 1. Differentiating WRT time. 2. Recall mole balance for batch reactor, Chapter 1. Rearranging and substituting into. 2. Design equation in terms of conversion. 2. Batch reactor design equation. Design equation, in terms of conversion, x. 3. What is the time required to achieve a specific conversion? Integrating, 3, with limits, t equals 0, x equals 0, t equals t, x equals x. 2. Batch reactor design equation. For constant volume batch reactor, V equals V0. Design EQ. From Chapter 1. Rearranging. Rewrite in terms of concentration. 3. Flow reactors design equation. Moles of A reacted. Middle dot. Moles of A reacted / consumed equals moles of A fed. Moles of A reacted. Time. Time. Moles of A fed. Middle dot. Equals, FA0, x. Molar rate at which A is fed to the system. Molar rate at which A is consumed within the system. Molar flow rate at which A leaves the system. FA, FA0, FA0x. FA, FA0, 1x, 3. Flow reactors design equation. FA, FA0, FA0x. Liquid phase is given in moles / dm3. Gas phase. Partial pressure. 3.1 CSTR FA FA0 FA0x. Recall design equation for CSTR, Chapter 1. 1. Substituting into 1. Rearranging. FA FA0 FA0x. 3.2 PFR FA FA0 FA0x. Recall mole balance for PFR, Chapter 1. 1. We know that, 2. Differentiating, 2, WRTX. FA FA0 FA0x. 3. Substituting, 3, into, 1. 4. 3.2 PFR. 4. Integrating, 4, with limit V equals 0 when x equals 0. 3.3 PBR design equation for PBR, catalyst weight, VW RA. Similar to that of PFR except those terms. Catalyst weight. VW RA. Summary of reactor mole balance. Differential form. Algebraic form. Integral form. Batch. CSTR. Dash. Dash. PFR. PBR. 4. Reactor sizing, CSTR and PFR. With a given Ra as a function of conversion, X, we can size any type of reactor. How? Construct Levenspiel plot. FA0/Ra versus X. Volume of the reactors can be represented as the shaded areas in the Levenspiel plots. 4. Reactor sizing. Consider a first-order reaction. A plot of 1/Ra versus X can be constructed. An infinite reactor volume is needed to reach complete conversion. 4. Reactor sizing. Use plot of 1/Ra versus X to size flow reactors for different entering molar flow rates, FA0. Important notes: for irreversible Rxn, A, greater than B plus C. 1. If the reaction is carried out isothermally, the rate is usually greatest at the start of the reaction, when the concentration is greatest, when X0, 1/Ra is small, Ra is big. 2. As X, greater than 1, Ra, greater than 0, thus 1/Ra, greater than, V greater than. An infinite reactor volume is needed to reach complete conversion. An infinite reactor volume is needed to reach Shay. 4. Reactor sizing. Important notes: count. For reversible Rxn, a B plus C. 1. The max conversion is the equilibrium conversion, Shay. 2. At equilibrium, Ra net 0. X, greater than Shay, Ra, greater than 0, thus 1/Ra, greater than, V greater than. An infinite reactor volume is needed to reach Shay. 4.1 Reactor sizing, sizing a CSTR. Example 1. Example 1. Calculate the volume to achieve 80% conversion in a CSTR. Given, species A enters the reactor at a molar flow rate of 0.4 moles per second. Solution. Find 1/Ra at X equals 0.8. 2. Calculate V. 4.1 Sizing a CSTR Levenspiel plot, X 0.1, 0.2, 0.4, 0.6, 0.7, 0.8 Ra 0.45. Example 1. Levenspiel plot. X 0.1, 0.2, 0.4, 0.6, 0.7, 0.8 Ra 0.45, 0.37, 0.3, 0.195, 0.113, 0.079, 0.05. FA0/Ra 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.00. 4.2 Reactor sizing, sizing a PFR. Volume of the PFR can be calculated using integration formulas. Trapezoidal rule, 2 point. Simpson's 1/3 rule, 3 point. Simpson's 3/8 rule, 4 point. 5 point quadrature formula. 4.2 Reactor sizing, sizing a PFR. Trapezoidal rule, 2 point. Simpson's 1/3 rule, 3 point. 4.2 Reactor sizing, sizing a PFR. Simpson's 3/8 rule, 4 point. 5 point quadrature formula. 4.2 Sizing a PFR. Example 2. Calculate the volume to achieve 80% conversion in a PFR. Given, species A enters the reactor at a molar flow rate of 0.4 moles per second. 4.2 Reactor sizing, Sizing a PFR. Recall the design equation of PFR. For x equals 0.8. 4.2 Sizing a PFR level spiel plot, x 0.1 0.2 0.4 0.6 0.7 0.8 Ra 0.45. Example 2. Level spiel plot. X 0.1 0.2 0.4 0.6 0.7 0.8 Ra 0.45 0.37 0.3 0.195 0.113 0.079 0.05 FA0/Ra 0.89 1.08 1.33 2.05 3.54 5.06 8.00 4.2 Sizing a PFR. Recall 5-point quadrature rule. Find h, x. 4.2 Sizing a PFR level spiel plot, x 0.1 0.2 0.4 0.6 0.7 0.8 Ra 0.45. Example 2. Level spiel plot. X 0.1 0.2 0.4 0.6 0.7 0.8 Ra 0.45 0.37 0.3 0.195 0.113 0.079 0.05 FA0/Ra 0.89 1.08 1.33 2.05 3.54 5.06 8.00 4.2 Sizing a PFR. Find V, substituting the numerical values. Greater than PFR with volume of 2.165 cubic meters is required to reach 80% conversion. 4.3 Comparing volume of CSDR and PFR. Difference BTWN CSDR and PFR volumes equals 4.235 cubic meters. PFR. 4.3 Comparing volume of CSDR and PFR. VCSDR greater than VPFR for the same conversion and RXN condition. Y. 5. Reactors in series. The exit stream of one reactor is fed to the next one. 5.1 CSDR in series reactor 1, mole balance, in, out plus generation equals 0. FA0, FA1 plus Ra1 V1 equals 0, 1. The molar flow rate of A at point 1. FA1 equals FA0, FA0 x1, 2. Combining, 1, and, 2. 1. 2. 5.1 CSDR in series reactor 2, mole balance, in, out plus generation equals 0. FA1, FA2 plus Ra2 V2 equals 0, 3. The molar flow rate of A at point 2. FA2 equals FA0, FA0 x2, 4. Combining, 3, and, 4. 1. 2. Expressed in EQ, 2, and, 4. 5. 5.1 CSDR in series FA1 equals FA0, FA0 x1, 2, FA2 equals FA0, FA0 x2, 4, 5. 1. FA2 equals FA0, FA0 x2, 4. 2. 5. Substituting 2 and 4 into 5. 5.1 CSDR in series. Example 3. X 0.0 0.1 0.2 0.4 0.6 0.7, 0.8. FA0/RA M3, 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.0. For the two CSDRs in series, 40% conversion is achieved in the first reactor. What is the volume of each of the two reactors necessary to achieve 80% overall conversion of entering species? For reactor 1, X equals 0.4. For reactor 2, X equals 0.8 by 0.0, 0.1, 0.2, 0.4, 0.6. Example 3. X 0.0, 0.1, 0.2, 0.4, 0.6, 0.7, 0.8. FA0/RA M3, 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.0. For reactor 1, X equals 0.4. For reactor 2, X equals 0.8. Total V equals 0.82 plus 3.2 M3 equals 4.02 cubic meters. Example 3. 5.1 CSDR in series. Levenspiel plot of CSDR in series. V2. V1. 5.2 PFR in series. V1. V2. The overall conversion of two PFRs in series is the same as one PFR with the same total volume. V1, PFR. V2, PFR, 5.2 PFR in series. Example 4. X 0.0, 0.1, 0.2, 0.4, 0.6, 0.7, 0.8. FA0/RA M3, 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.0. Calculate the reactor volume V1 and V2 for the plug flow sequence shown below when the intermediate conversion is 40% and the final conversion is 80%. Using Simpson's 1/3 rule. X 0.0, 0.1, 0.2, 0.4, 0.6, 0.7, 0.8. FA0/RA M3, 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.0. Using Simpson's 1/3 rule. For reactor 1, X equals 0.2, X0 equals 0, X1 equals 0.2, X2 equals 0.4. For reactor 2, X equals 0.2, X0 equals 0.4, X1 equals 0.6, X2 equals 0.8. Total volume, X 0.0, 0.1, 0.2, 0.4, 0.6, 0.7, 0.8. FA0/RA M3, 0.89, 1.08, 1.33, 2.05, 3.54, 5.06, 8.0. For reactor 2, X equals 0.2, X0 equals 0.4, X1 equals 0.6, X2 equals 0.8. Total volume 5.3. Combination of CSDR and PFR. V3, CSDR. V1, CSDR. V2, PFR. X1, X2, X3, 5.4 Reactor sequencing. Which sequence is better to obtain the highest overall conversion? Or, the best sequence of reactors depend on Levenspiel plot. Reactor size. Measures entering flow rate at the entrance condition. 6. Space-time. Measures entering flow rate at the entrance condition. Space-time/mean residence time. Time taken for a fluid to either completely enter or completely exit the reactor. E.g., if V equals 0.2 cubic meters, V0 equals 0.01 cubic meters per second, what is tau? Answer: tau equals 20 s. 7. Space velocity. SFOW. Space velocity can be defined as two types of SFOW that is commonly used in industry. Liquid hourly space velocity, LHSV, measures liquid volumetric rate at 60 degrees Fahrenheit or 75 degrees Fahrenheit. Gas hourly space velocity, GHSV, measures gas volumetric at standard temperature and pressure, STP. Summary conversion, batch reactor, flow reactors design equation. Batch, CSTR, PFR, PBR. Reactor in series. Conversion, CSTR in series, PFR in series. Exercise. The irreversible gas phase non-elementary reaction A plus 2B, greater than C is to be carried out isothermally in a constant pressure batch reactor. The feed is at a temperature of 227 degrees Celsius, a pressure of 1013 kilopascals, and its composition is 30% A and 60% B. Laboratory data taken under identical conditions are as follows. A. What is PFR volume necessary to achieve 30% conversion for an entering flow rate of 2 cubic meters per minute? Ra, mol/dm3.s 0.00001 0.00005 0.00002 0.00001 x 0.0 0.15 0.3 0.6 Exercise. A. What is PFR volume necessary to achieve 30% conversion for an entering flow rate of 2 cubic meters per minute? Given. We know that in for gas phase. 1. Find CA0. 2. Find FA0. 3. Calculate VPFR using integration rule. Exercise using Simpson 1/3 rule. Ra, mol/dm3.s 0.00001 0.00005 0.00002 0.00001 x 0.0 0.15 0.3 0.6 FA0/Ra, DM3 243,000 486,000 1,215,000 2,430,000 Using Simpson 1/3 rule. Exercise. Ra, mol/dm3.s 0.00001 0.00005 0.00002 0.00001 x 0.0 0.15 0.3 0.6 FA0/Ra, DM3 243,000 486,000 1,215,000 2,430,000 B. What is CSTR volume necessary to take the effluent from PFR above and achieve 60% total conversion, based on species A fed to the PFR? FA0 equals 2.43 moles per second. X equals 0.3. X equals 0.6.